Okay, folks, we can get going. Any questions from anyone at this point? The Monday lab section seemed to go pretty well overall. Sort of as expected, I mentioned that the first week's checkoff is a little bit light, and so perhaps predictably, folks wrapped up that lab checkoff rather early and had the opportunity to work ahead a bit on next week's checkoff, which, by the way, is the right way to do this class. And so if you can maintain that pace throughout the semester, that is, in my opinion, the way to get the most value out of this class. That is to say, if you can manage to be working ahead of lecture a little bit so that you're doing the reading and some of the figuring out of things on your own and then coming to lecture to have that stuff clarified or reinforced, that's a way to really get a lot out of the class, as opposed to the opposite direction where stuff is introduced here and then you go do it in the lab. If you can try to maintain that flipped way of doing it, I think it's really productive. Something else I wanted to just mention, I'm speaking with the TAs. We're going to open up some extra lab hours on Sundays. I'll post on Ed or someplace precisely when those hours will be. Those will be TA-run lab sections. Yeah? It's on all the lab write-ups. On each lab assignment, there's a reading section. So we're going to open 3 hours of open lab on Sunday. The idea there is just it's more time for you to come to work. I'll mention, I think I mentioned this perhaps, I'm not sure if I explicitly stated this before, but I'll just state now. A lot of the design of this class and the infrastructure of this class, things like this VS Code build environment and these little kits that you can take home with you and these extra lab hours, the whole idea is to try to remove a time pressure from your engineering design experience. I am not interested in evaluating your ability to do engineering subject to severe time constraints. It doesn't strike me as very realistic outside of like Apollo 13 or something. You know, when again will you have to design and build something in an hour and a half? And that stress, if you're trying to do that, makes it hard to learn this stuff. So the course is designed to try to allow for you to try to eliminate that time pressure. So you can take your kits home. All of your build environment stuff is supposed to be compatible with your own laptop, so you can work on this at your own time. There will be extra lab hours on the weekend. So hopefully the opportunity is there to relieve some of this time pressure from yourselves in the design problem. Now, in order for that to be true, you have to do this stuff outside of class, and so please do it so that you're not stressed. But I'm trying to set it up so that you can do this in an unstressed fashion, because I think that's how you learn the most from the class. Okay. I will just very briefly remind you that what we are doing this week is incrementally building ourselves up to the demo code from which you will begin your lab checkoff next week. The content that we have to cover includes timers and timer interrupts, which we went over last time, SPI channel communication, which we went over last time. We have to cover the direct digital synthesis algorithm, which we're going to do today, and proto-threads, which we'll probably do on Friday, and a keypad, which will be Friday or Monday. So I'll just very, very briefly remind you, the strategy that we started with last time is to go through this direct digital synthesis demo code. Our first pass was just looking at structure. Where is main? Where's the interrupt service routine? How do we set up the peripherals? What I'd like to do now is go back and talk about the algorithm that this actually implements, which is direct digital synthesis. And so last time, you'll remember that I was kind of waving my hands at some of the variables and some of the math and saying we'll come back to it. We're going to come back to that now. And so this is the code that we've been looking at. We're going to come back and look at this, but before we do, I want to talk about the algorithm separate from the code, and then we'll come back to the code to substantiate what we're going to talk about. So direct digital synthesis is the algorithm in question. This is a really good one for your toolkit, like a really, really good algorithm to understand deeply. The reason is, you know, you could imagine coming up with some metric that describes the power of an algorithm that's something like the ratio of what it delivers versus what it costs in terms of hardware resources or CPU time. This is off the charts in that what it delivers, as we'll see, is the ability to produce a sine wave, or really any other periodic waveform, of a desired frequency with remarkable precision. As we'll see, you'll be able to generate a sine wave of a desired frequency to within fractions of fractions of fractions of hertz. And what it will cost us in terms of resources for this project is an array of ints that's 256 elements long. That's almost nothing in terms of memory requirements. And 2 lines of code in an interrupt service routine. And that's it. And then what it delivers is this amazing ability to produce waveforms. So that's what we're going to be talking about. I want to talk about this by reminding you of something that probably you don't need to be reminded about, but perhaps it's been a while since you thought about this, which is, what is a sine wave? Let me just remind you that what a sine wave is the projection onto the imaginary axis, that is to say the vertical axis, of some rotating phasor. And so this is a picture of a rotating phasor, a rotating unit vector, and as it rotates, you can see the projection onto the imaginary axis in green here, and what streams off is a sine wave. The central observation to this algorithm, the clever observation, which is an obvious one, but as we'll, well, it's only obvious in retrospect, right? But the central observation is that we can describe the position of this phasor, that is to say the angle at which it currently resides, as illustrated by that little red arc there. We can describe that in a number of different units. So, you know, if the phasor is about oh, you know what I'm saying. Let's see. If the phasor is at approximately 90 degrees, we could say that phasor is at 90 degrees. We could alternatively say it's at pi over 2 radians, and it means exactly the same thing. The clever observation with direct digital synthesis is we can come up with a new unit for angle that has some very useful properties for our purposes. So what we're going to do with direct digital synthesis is describe the position of this phasor in a new unit that we're going to come up with. We're going to call this accumulator units. And we are going to say that there are 2 to the 32 accumulator units per rotation. So there's 360 degrees per rotation. There's 2 pi radians per rotation. There's 2 to the 32 accumulator units per rotation. The cleverness of this is, in our C program, if we choose to store the position of this phasor, that angle, in an unsigned int, we can hold values in that unsigned int of 0 up to 2 to the 32, right, which is exactly the amount of units that describe one rotation. What that suggests is, in our program, if we add to that variable, that is isomorphic to, that is to say it can be thought of as rotating this phasor, and when we add from 0 all the way up to 2 to the 32 minus 1, and then we add one more and it overflows, the phasor ends up exactly where we want for it to be. That is to say, the overflow becomes not something we have to worry about, but actually a feature of our unit. We can just add and add and add and add, and as we add, that can be thought of as this thing rotating around. And when we get back to the beginning, where it wraps back to 0, exactly the right behavior occurs. That's the clever observation. Are there any questions about that? So what this picture is showing is the angle of that phasor in radians, the same angle of that phasor represented in these accumulator units, written out in binary just to show you that there's 32 of these bits, okay? But so far, all we're doing is saying we have a new unit for angle. There's 2 to the 32 of them per rotation. That gives us this handy ability to just add and add and add and not worry about overflow. People okay with that? So then, what I'd like to discuss, I think this is the right way to introduce this. What I'd like to talk about is the steps of the direct digital synthesis algorithm first, and then I'm going to go back and substantiate each of those steps with a little bit of analysis. I think that's the clearest way to do this. So, when you're conducting audio synthesis, when you're producing a sound, it is a requirement in order for that sound to sound correct that you do that synthesis at a very precise rate. In Lab 1, we are going to be doing audio synthesis at 50 kilohertz. So that means 50,000 times a second, you're sending a new voltage out to the DAC. The reason that we have to be precise with our timing with audio synthesis is your ears, as it turns out, are rather sensitive instruments, particularly to this kind of thing. And so if you have errors in your synthesis rate, you will hear that as artifacts. It's one of the nice features of this lab is you can't really trick yourself if you're getting it wrong. Okay? You'll hear the problem. Okay, so in order to enforce that timing, we're going to use these alarm interrupts that we talked about last time. So we'll schedule some code for execution for 1/50,000th of a second in the future. That code will execute, and then we'll schedule that code again for another 1/50,000th of a second in the future. And we'll keep scheduling this over and over and over again. Each time you enter the interrupt service routine associated with that alarm, you're going to go through the following steps, which we're going to talk about in detail. So you enter the alarm interrupt service routine. In the event that you are modulating your frequency, i.e. producing a bird song where the frequency sort of swoops and goes like this, the first thing you do when you enter your interrupt service routine will be figure out what frequency do I want to synthesize now as a function of time. If you're producing a pure tone, as this example is, we don't worry about that. We're just producing the same tone all the time. But okay, in the event that you're producing a modulated frequency, you figure out what frequency you want to synthesize. The next thing that you do is you increment that accumulator, that unsigned int that you're using to store the position of this phasor as it rotates. You increment that by some amount. And remember, like I just talked about, incrementing the phasor is the same as rotating it, given our clever choice of units here. So you enter the interrupt service routine. In the event that you're modulating your frequency, you figure out what frequency you're going to modulate. Then for that frequency, you add a little bit to your variable that's holding your phasor angle, which rotates it a little bit. You take that new position of the phasor and go into a sine lookup table that says for each position of the phasor, it tells you what the amplitude of the associated sine wave is. So you go look that up, get your sine wave value out, the amplitude out. You send that off to the DAC. That's an SPI transaction. Reschedule your alarm so that that happens 1/50,000th of a second in the future again, and then the whole process repeats. You re-enter the interrupt service routine, add a little bit to your accumulator, which rotates this phasor a little bit. Go look up the sine wave amplitude, send it to the DAC. Then do it again. And perhaps obviously, the more that you add to that accumulator each time you enter the interrupt service routine, the faster this phasor is rotating, and hence the higher frequency the output sine wave. If you add less to that accumulator each time, that means you're rotating the phasor less each time you enter the interrupt service routine, and the output sine wave is lower frequency. And so the obvious question is, for a desired output frequency, say you want to generate middle C, is that 262 hertz? Say you want to generate exactly 262 hertz, the question is, well, by how much should I increment the accumulator each time I enter the interrupt service routine? That is what the direct digital synthesis algorithm tells you. For a desired output frequency, it tells you how much you should rotate that phasor each time you synthesize a new sample for the DAC. Now that, of course, is an equation, which I could just present to you, but I thought it might be kind of instructive to build our way up to that equation so that you could perhaps have something like an intuitive sense for where it comes from. So the question that we're going to now answer, we're going to work our way to the equation that answers the question is, for a desired output frequency, by how much do we increment that accumulator, that unsigned int that we're using to hold phasor position? Like I said, we're going to work our way to the answer. The way to start working our way to the answer is just, let's suppose, let's ask some questions not about, let's reverse the question a little bit. Rather than asking, for a desired output frequency, how much should we increment the accumulator? Let's instead ask, if we increment by this much, what's the output frequency that we get? And we can identify a relationship. By the way, I sound sick. I'm actually not, or at least I don't think I am. Every semester at the beginning of the semester, I don't talk that much between semesters. I'm mostly like in dark corners, dorking around with microcontrollers. And then the semester starts, and I'm suddenly talking 7 hours a day. And it usually takes like 2 weeks for my voice to catch up. So that's why my voice sounds a little wonky. So in any case, let's suppose that every time we enter that interrupt service routine, we just incremented the accumulator by 1, just by 1 unit. And then let's ask, what would be the output sine wave frequency that we would get? And we can arrive at the answer to this question through straightforward dimensional analysis. So we know that one overflow of our accumulator, that is to say, 1 sine period, is equivalent to 2 to the 32 of our accumulator units. We're imagining that every time we enter the interrupt service routine, we're going to increment that by 1 accumulator unit. So that's 1 accumulator unit per audio sample, per synthesis sample. And then we're going to do fs in lab 1 for you. That's going to be 50,000 kilohertz. We're going to do fs of those audio samples per second. And what comes out at the other side is we find that our output sine wave has a frequency of our synthesis rate fs divided by 2 to the 32 hertz. So if you were to increment this by 1 unit every time you enter the interrupt service routine, let's say you're doing that 50,000 times a second, you end up with a sine wave with a frequency of 10 to the minus 5th hertz. So that's 1 sine wave every 85, close to 89,000 seconds. About 1 period of a sine wave per day. That's pretty darn low frequency, right? So if you were to only increment that accumulator by 1 every time you enter the interrupt service routine, you will generate a sine wave that goes through 1 period per day, if I'm doing this quick math correctly. All right, let's say instead that we incremented it by 2 accumulator units every time we enter the interrupt service routine. Exactly the same analysis. We get 1 sine period every 2 to the 32 accumulator units. We're doing 2 accumulator units per audio sample. We're doing fs, 50,000 in your case, of those per second. And we end up with fs over 2 to the 32 times 2 hertz on the output. And then, of course, the obvious next step is to generalize this. Let's suppose that we produce some arbitrary number of, we increment by some arbitrary amount j. That's a typo. That should be n. It's easier if it's n. Make that n. Let's say we increment by n accumulator units per audio sample. Well, then what we get on the output is our synthesis rate over 2 to the 32 times n hertz. And now you can look at this expression and ask yourself, what are the knowns and the unknowns here? If you are interested in producing a sine wave of a desired frequency, middle C, 262 hertz, then you know f out because you specify that. That's what you want, right? So you say 262 hertz or 400 hertz or whatever you want there. You know that. You know your synthesis rate, fs, because you set up the timer interrupts. In lab 1, you're going to set this up such that fs is 50,000. That's not a sacred number, by the way. You could use different numbers, but in lab 1, I'm specifying 50,000, 50 kilohertz as their synthesis rate. 2 to the 32 is a constant, so obviously we know that. So the only unknown here is n, the amount by which we increment. So what that means is if we want to know the amount by which we should increment for a desired output frequency, all we have to do is rearrange this equation. And so for a desired output frequency, the amount by which we increment every time we enter the interrupt service routine is our desired output frequency divided by our synthesis rate times 2 to the 32. So those of you that may have been poking around the demo code for lab 1 or that may have a good memory about the code we were looking at last week, you may remember a line in there where a certain variable had f out over 2 to, we'll see that in a moment, but that's where this comes from. Okay, so this tells us for a desired output frequency how much we need to increment. So let's do a quick example here. Are there questions about that? Yes?
What determines the frequency, like the fs?
So what determines your synthesis frequency? It relates to the highest frequency that you're interested in synthesizing. Bruce, did you have something you want to say about that? So let's say you want to synthesize a kilohertz. Probably want at least 10 times that for your f out. Relates to the Nyquist theorem. Any other questions about this? Okay, so let's just look at a quick example. Let's suppose you want to generate 262 hertz, middle C, and let's suppose you're using an audio synthesis rate of 44 kilohertz, which is not what you're using in lab 1, but just for an example. By how much should you increment the accumulator every time you produce a sample for the DAC? Well, our desired output frequency is 262. Fs is 44,000, multiply it by 232, and you end up with this number, 25,574,577. So if every time you enter the interrupt, if you're entering it 44,000 times a second, if you increment the accumulator by that number and look up the associated sine wave amplitude and send it to the DAC, you are going to get 262 hertz out. This raises some questions. One of the questions that it raises is, okay, let's say we're trying to produce middle C. How close are you getting? You're not producing exactly 262 hertz, but plus minus how much are you producing that? And we actually kind of already answered this question. Another way of framing that question is to ask how much frequency is contained in 1 unit of accumulator. It's another way of asking the equivalent question, which we just did the little math to figure out. In the case that you are doing a synthesis rate of 44,000, that comes out to something like 1 times 10 to the minus 5th hertz, which, as we just saw, is something on the order of 1 sine period per day. So that is to say, for that synthesis rate, if you ask for 262 hertz, you will hit 262 hertz plus minus that many hertz. Is that not astounding? It's astounding how well that works. But here's an interesting question. This whole time I've been supposing this accumulator unit for angle and saying, you know, what if we had 2 to the 32 of them per rotation? That is, say, an unsigned int. Another question you may ask is, well, why an unsigned int? Why don't we use an unsigned short, 16 bits? If we used a short, you could go through exactly the same analysis, and what you would find is, for each single unit of accumulator, there are 0.67 hertz. So that means if you're using a 16-bit unsigned short to hold your phasor angle, and you ask for 262 hertz, or whatever frequency, you'll get your desired frequency plus minus that amount. What if you used 8 bits? Well, then again, exactly the same analysis shows you get positively abysmal precision, right? You won't be able to hit a desired frequency to better than 171-ish hertz. I'm going to add some clarity in a moment as to some intuition as to why that's the case. Okay. Another question you may have is, I keep saying, you know, we were looking at this picture up here, and what I said was the order of operations is you enter the interrupt service routine, you rotate that phasor by some amount. We just figured out the equation that tells us how much we increment that phasor in order to produce a desired frequency. That moves the phasor to some new position, and then I said we go look up the sine wave amplitude at that position. Now, if you're using an unsigned int to hold that phasor position, that means it can assume 2 to the 32 different values as it goes around. Does that imply that we need a sine wave table that is 2 to the 32 elements long? Thank God, no, right? Because that would make this completely impractical. You can get away with a sine table that is significantly shorter, that includes significantly less entries than you have units of accumulator for 1 rotation. There's a trade-off that occurs, and I want to illustrate that trade-off by way of another little animation down here. So what we're looking at down here is what we're doing here is we're considering sine wave tables of different lengths. So here, for instance, is a picture of a sine wave table of length 8. So you can see this is 1 period of a sine wave, and our 8 table entries correspond to the amplitude of that sine wave at 8 evenly spaced points. That gives us this kind of squared off approximation of a sine wave. What we're looking at below this is the power spectrum associated with that sine wave. If this were a pure sine wave, what you would expect to see in the power spectrum, in these sort of normalized units that I'm using, is totally flat at all frequency and a big spike of power at 1 in these units, which is to say the frequency of the sine wave. In this power spectrum, we do see a spike at the fundamental, the frequency of this sine wave, but then we see a bunch of other harmonics here. And that's because of this squared off business, right? Because what we're producing is not actually a pure sine wave. You could think of it as a fast square wave being modulated by a slower sine wave or something. And you may remember again from calc class or something, if you think about the Taylor series expansion of a square wave, includes a whole bunch of different sine terms, and it's all of those sine terms that we're seeing here in the power spectrum. And so the way to answer the question, how big does my sine table need to be, that really becomes a question about your requirements as they relate to your error harmonics. As we increase the length of this sine table, what you will notice is that the first error harmonic moves up in frequency and it attenuates, it shrinks. And so, let's see, by the time we get to, about, let's see, 100 entries, the fundamental in our power spectrum remains at the frequency of this sine wave. Our first error harmonic has moved up to about 100 times the frequency of the fundamental, and it has attenuated. So what are your requirements for lab 1? Well, your requirement is, it's a little bit squishy, but it has to sound like a bird. One way to maybe re-articulate that requirement is the first error harmonic has to be inaudible. Does anybody know their own cutoff frequency? What's the highest frequency that you guys can hear? 16 to 20 kilohertz, probably. I measured mine before a lecture, and I'm at 17 kilohertz right now. Bruce, do you happen to know yours? 9 kilohertz? This is if you are interested in such things, it's interesting to study your own sensors as kind of engineered systems and how their qualities change over time. Bruce? You have a pole at 3 kilohertz. Okay. It's interesting to study the frequency response of your own ears, right? So if you're into such things, something you might consider doing is on New Year's Day every year, measure your cutoff frequency, make a note of it, and then plot that throughout your life. And what you will see is how your frequency response changes with time. Yours are 16 to 20 kilohertz. So that is to say that if your first error harmonic is above 20 kilohertz or so, nobody's going to hear it. This, by the way, does anybody have, I have memories of being in elementary school and the TV's on, and it's making a very high-pitched whine, and the teacher can't hear it. That's why. The teacher is older, and their cutoff frequency has come down a little bit, and so it's super audible to them. They can't hear it, but the children can generally hear it. And that's why someone always raises their hand, and they turn it off, and the whole class goes, ah, right? And the teacher makes some joke about it. Okay. So for us, hopefully this substantiates that a 256 length sine table is plenty long for our purposes, right? The first error harmonic is going to be way above what is audible, and furthermore, it's going to be so attenuated that you're not going to hear it anymore. Okay, so here's another question, though. Let's suppose that we're using a 32-bit long variable to hold the accumulator value. We have 2 to the 32 accumulator units per rotation of the phasor, but our sine table is only 256 elements long. How do you associate an index of the sine table to one of the values of the accumulator? Because you have way more of the accumulator values than you do sine table entries. The easiest way to do this, the correct way to do this, is you use the most significant 8 bits of your accumulator value to index into your 256 element sine table, right? Those 8 bits go from 0 to 255. You just use those to index right in. So again, we'll see this in code, but those of you that have been poking around with this or remember from last time, you may remember that right before we do the transaction to the DAC, there's a shift right by 24 to index into the sine table. We're shifting out all this stuff so that we just retain the top 8 bits. Now this sometimes causes confusion in that naively you might look at this and say, well, if we're only using 8 bits, what the heck's the point of having the rest of these 32 bits? As we saw, when you shrink the size of this accumulator from 32 to 16 to 8 bits, you lose resolution in your synthesizer. A way to think about this is, we've been talking about that accumulator as describing the position of this phasor, which is a correct way of thinking about it. Another way of thinking about it, which is equally correct, is that accumulator describes, it is telling you the index into which to go access the sine table with fractional precision. So this allows for us to say that we are currently at index 8.005 blah, 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 with a whole bunch of precision. Now, of course, you can't fractionally index into a sine table. When you index in, you go get the integer part. But by keeping track of fractional amounts of index, it allows for us to move from one index to the next one at exactly the right time, because we're able to keep track of just the right amount of index each time so that we move to the next one at exactly the right time. And that's where the precision comes from, the high resolution comes from. As you sacrifice these fractional bits, you lose the ability to move to the next index at the table at exactly the right time. The practical consequence being you lose resolution in your synthesizer. So that's why we're retaining these extra bits. Okay, so some common questions, some of which we've already answered. This one actually I exactly just answered. You need more than 8 bits to maintain fractional index information. Another question here. Let's suppose that you were tremendously memory constrained, right? And also, you have severe requirements with regard to your error harmonics. Like, let's suppose you're so memory constrained that you can't manage a table longer than 30 entries. A pretty extreme situation, but maybe. But also, at 30 entries, this error harmonic, it doesn't meet your requirements. This is too loud. What would be one answer? Interpolation would be one answer. That's a cool idea. Sure, turn it into a feature. Are you a musician? Yeah. Okay, I can tell. What I was sort of alluding to is, let's suppose if you wanted to just get rid of this, and you couldn't afford to do a software trick for that because you're memory constrained or time constrained or whatever it may be, put an RC low-pass filter between your DAC and the speaker, right? And then you get to pick whatever the cutoff frequency of that RC low-pass filter is.
You know that once you have sort of a quarter wave, sine wave, you can replicate it 4 times, so you can sort of get away with 1/4 memory usage if you trick it one time.
You guys are too smart, but yes, that works too. But what I'm trying to suggest is, don't forget about hardware when you're doing these design problems. It's often the case that careful use of hardware, strategic use of hardware, makes your software a lot easier. It can be a temptation to try to oversolve problems in one domain versus another domain. And I'm just encouraging people to keep their minds open that these problems can be solved sometimes in hardware, sometimes in software, and the most elegant solution is often a combination of the two. Okay. So then, all of this, how much time do we have? Okay, great. So before I move on to the next thing I want to talk about, which is, let's suppose you want to produce a modulated frequency with time or a bird song, let's just pop back very quickly to that code that we were looking at last time so that we can fill in some of the gaps, some of the things that I waved my hands at. So last time we started at the top, we just started going through this. Some of the things that I kind of waved my hands at last time were things like alarm number and alarm interrupt. We now know that alarm number is 0 because we're using alarm register 0. There's 4 alarms, we're using the 0th one. We know that alarm interrupt is timer interrupt 0 because we looked at that interrupt table and we said, that's the interrupt associated with that alarm. So that's what those two numbers mean. We know why 2 to the 32 is here now. It's for direct digital synthesis. Fs, our sample rate, we have set to 50,000. Our delay, we have set to 20. That's 1 over Fs in microseconds. That is to say, we want for our interrupt service routine to fire every 20 microseconds, 50,000 times a second. We have 2 variables here. One, unsigned int called phase accum main. That's our phase accumulator. That's the variable that is holding the position of that phasor. It's an unsigned int. We have another one called phase increment main, which is being set to 800 times 2 to the 32 over fs. This example is producing a pure tone at 800 hertz. That is the encoded implementation of the equation that we just derived. So that's telling us how much we need to increment every time to produce 800 hertz. If you want 400 hertz, you just change the 800 to a 400. You get some big crazy number out that looks like nothing, right? But you increment by that number, you get exactly what you need out. The unsigned short DAC data, that's a 16-bit value. That's where we are holding the data that we're actually going to transmit to the DAC. 16 bits because we looked at the DAC data sheet and we saw it expects 16-bit transactions. So we're going to hold that data in an unsigned short, or a uint 16_t. DAC config channel A and DAC config channel B. Each of these are 16 bits long. The top 4 bits are those configuration and control bits that we saw in the data sheet. The bottom 12 bits are where we're going to put the data that we're actually going to send to the DAC. It's 12-bit DAC. We have our GPIO selections. These come from the pinout diagram for the Pico. For each of these signals, we looked at the pinout diagram and said, okay, what is our menu of GPIOs that we could choose from? And we chose some of them. We're going to use SPIO channel 0. Okay, some more DDS stuff. Our sine table size is going to be 256. That's how big our sine table is going to be. Why? Because that makes our error harmonics inaudible. We could probably get away with shorter than that, right? But we're just going to make it 256. And then, of course, we declare our array of ints that will hold all of the amplitudes of that sine wave over one period. And then, right, main's down here. We already looked at main. But let's take a look at this interrupt service routine that we are entering 50,000 times a second. Every time we enter this interrupt service routine, you'll see at the very first thing we do and the very last thing we do is we set a GPIO high at the beginning and low at the end. This is just so that you can use the oscilloscope to probe that GPIO, and you'll be able to measure with the cursors exactly how much time you're spending in this interrupt service routine. You'll be challenged to minimize it. We're going to talk about some sneaky ways to do that. But we'll be measuring the speed of your code directly with the oscilloscope. Okay, next thing we do is we clear the interrupt. So an interrupt fired to get us into this interrupt service routine. It's actually our responsibility as the programmer here to reset that interrupt and to clear it. So we clear it. We reset the alarm register to schedule this code for execution 20 more microseconds in the future. That happens right there. That sets our deadline. We better get out of this interrupt service routine before that fires again. And then all of direct digital synthesis is these two lines. We increment our phase accumulator by that value that we computed to be the one that's required to generate, in our case, 800 hertz here. We look up the sine table at that phasor position by right-shifting phase accumulator by 24. That just gives us those top 8 bits. We interpret that as an index value and just go get the value out of the sine table, mask it into our DAC configuration, and send it off to the DAC. By the way, the plus 2048 there, we'll see in a moment down further, when we build the sine table, it is centered around 0, goes to positive values, negative values. The DAC accepts values between 0 and 4096, so we just level shift it up as a last step. The reason we don't do that down at the sine table, you could, is just sometimes convenient to have your sine table values centered around 0 for like doing math, because that's what you mathematically expect. So we do that as a last step. SPI write 16 blocking, that is a C SDK function call that's writing a register associated with the SPI peripheral that says, please take this data that we're pointing to, that's a pointer to DAC data, it says, please take that data and over that SPI channel, do one transaction. And then the SPI channel sees that and it sends it. SPI write blocking means that our application code will stall here until the SPI peripheral tells us, I finished that transaction that you asked for. Put the GPIO low, code enters back into main and continues to do application stuff. 1/50,000th of a second later, we do it all again. And this will produce a pure tone. What I want to talk about next is how do we produce a modulated tone? But that's actually very simple, as it turns out. This is really the nuts and bolts of this algorithm. So it's kind of amazing, right? This cost us an array of ints that was 256 elements long, could honestly even be shorter, given our requirements, and 2 lines of code, and we get exquisite sine waves. Okay. So, but you're not producing a pure tone in this lab. You're producing modulated tones. You're producing this sequence of frequency sweeps. What we're looking at in particular are the dark lines here. There's a little bit of very low amplitude harmonics. We're just producing the dark lines here. So what we're going to do is look at each of these frequency sweeps and fit them to functions. So for instance, the first little whoop there at the beginning, that kind of looks to me like the top of a sine wave. Maybe it looks like a parabola. Probably either would work. That part there kind of looks to me like a parabola. And so what we'll do is take each of those and largely by eye, there's a time axis down here, or up there actually, and there's a frequency axis there. And so you can put this in PowerPoint or something and draw 2 points and kind of eyeball, okay, it goes through this frequency at this time, this frequency at this time, this frequency at this time, and solve for the unknowns in your sine equation or your parabola equation or whatever it may be. Right, so that's what we're doing here. So we're saying that first little swoop part, that kind of looks like some sine wave with an offset. So some equation of the general form k sine mx plus b. I'll mention the most useful units of time to use here are interrupts. So you could use seconds, but that's kind of inconvenient. A very convenient unit of time to use is interrupt, so that every time you enter the interrupt service routine, you just increment by 1, and that's 1 more unit of time, 1 more unit of time. If you do all your math in those units, it makes your interrupt service routine arithmetic way simpler, because you're just counting in the natural unit of the equation that you're using. So in any case, this is the equation we're going to fit to. We figure out a few points that we go through so that we can solve this, solve for all these unknowns in the equation. And you end up with some equation that describes y here is the output frequency as a function of x, the time in interrupt units. Now, something I put in ed that I want to just point out because it's easy to overlook, this write-up, and there's an associated separate page that describes birdsong synthesis and derives all these equations. In those, the write-up assumes a synthesis rate of 44 kilohertz, which is different from what you're asked for in lab. The idea here is I want to provide you all the mathematical infrastructure, but invite you to actually do this analysis yourself, right? And so all the nuts and bolts are there, but you'll have to redo some of this at the appropriate synthesis rate. I chose 50 kilohertz to be slightly sneaky with you all too. I think at 50 kilohertz, I'm not sure that you'll be able to meet timing deadlines with floating point arithmetic. Maybe you will, but you'll probably have to use fixed point, which we'll talk about in a coming lecture. So in any case, you get this function of frequency with respect to time, where time is just an incrementing variable in your interrupt service routine. The other thing that you will have to do is you're not producing constant tones, you're turning sounds on and off. Every time you turn a sound on or turn a sound off, you can't just cut it off or cut it on. You can't go from no sound to a full amplitude sine wave to no sound. Well, you can do anything. The consequence of doing that is, again, you can think about this again in sort of a Taylor series sense. What you're producing in that case is a full amplitude sine wave modulated by a step function. Think about the sine waves that compose the Taylor series of that step function. You'll remember from like Calc 1, there's a whole bunch of them, right? When you produce that sine wave modulated by the step function, you don't just hear the sine wave you're producing, you hear all the components of that Taylor series. And what it sounds like is a click or a pop. And so if you were to do that, you would hear click, swoop, click, and it would turn off. And that's annoying. And so we don't want to do that. Another way to think about this is we're sending values to a DAC, a digital to analog converter. That DAC communicates with a speaker. So it's sending analog voltages to a speaker. Inside of that speaker is a physical membrane that vibrates to set up pressure waves that go into our ears, that vibrate our eardrums, that produce sound, right? So it's a physical membrane. where every voltage that you send to that membrane corresponds to a position of the membrane. If you go from nothing, membrane is just here, to full amplitude, you're telling the membrane go from here to here. And what it will do is go boing, and that boing sounds like a click or a pop. It's actually an equivalent statement. Those two statements I just made are equivalent. That boing is a bunch of sine waves. Those sine waves you could think of as being the Taylor series components of that step function. Like I said, in this lab, that's a bug. Birds don't do that, right? Birds ramp on and off, so we better ramp on and off too. But it's not always a bug. Sometimes that's a feature. In lab 2, for instance, you have to make a little thunk every time a ball strikes a peg in that Galton board. When a ball strikes a peg, there's a bunch of frequency stuff happening there in a physical system. And so actually turning on a sine wave very quickly and turning off the sine wave very quickly, to my ear, sounds very physical for that system. It does not sound physical for this system. So there's never anything wrong. You just have to understand the consequences of everything you do. And sometimes those consequences are what you want, and sometimes they're not what you want. In our case, we want nice, smooth ramp on and off of sound. And if you do that, you end up with a little swoop. I want to just clarify, too, that in the write-ups that describe how to do this, the algorithm is presented in Python, and all of the amplitudes for the swoop are pre-computed and then played back at audio rate. You are going to be computing them in real time. You're building a synthesizer, not a playback machine. Right? So just to avoid any confusion, this is kind of a playback machine. You're making the synth version. Questions about any of this? Let me just mention, because it's too fun not to, you can play all kinds of fun games with direct digital synthesis. I've had some master students in the past do some really interesting things with this. I had one student in particular, let me find it. This student played the chimes, actually, and made the observation that there's a bell missing from the belfry. Do you know which one it is, Aiden? Low? C sharp. Okay. He was of the personality that this bothered him deeply. And he was very interested in learning what would this belfry sound like if I could write songs that included this. And so what he did is he took a microphone up into the clock tower and listened to the bell, recorded the bells on either side of the missing note, and interpolate them to come up with the frequency, the imagined frequency components of this missing bell. That looks like some spiky power spectrum. And he said, okay, I'm just going to look at each of these spikes, ignore the low amplitude stuff, but let's just look at each spike, and let's make a direct digital synthesis synthesizer that produces a sine wave of just that frequency. And then he looked at it over time and studied how all those spikes decay relative to one another for these particular bells. So he had not one synthesizer like you'll have in this lab, but he had, I think, maybe 15 of them or so. Played them all at once, so you hear all the frequency components at once, and then decayed them in a physical way so that they decay correctly relative to one another. And here's the real bell recording. It's from the clock tower. Here is his purely artificial synthesized bell using direct digital synthesis. It's pretty darn good, right? He too, by the way, he had a very good ear. He would come to our meetings like depressed to be like, I can't get it to match. I can't get it to sound right. And then he'd play these two things and go, what are you talking about? Like, it sounds exactly like the real bell. But he could detect these little differences. You can do other fun things. I had one student who modulated the frequency of a direct digital synthesizer using a mathematically chaotic system. The Lorenz system, those pretty butterfly curves. He set the frequency of that using the system. The thought here is our ears are very good at picking up patterns. This is an observation that's been made in by some folks in it's been made by some folks that do things like study DNA. There's one of the things you want to do with DNA is try to find the patterns. It's one of the things that's interesting about it. How do you find these patterns in DNA? One way that you can do it is you make plots of the A's and T's and U's and G's and so forth, and you look for the patterns. A clever thing that you can also do is say, all right, well, we've only got this many base pairs. Let's associate a musical note with each of them and listen to DNA. And it turns out that your ears are sometimes better than your eyes at finding patterns. The thought experiment here was, if it's the case that our ears are pretty good instruments for pattern recognition, are they also good instruments for the opposite, for chaos recognition, the mathematical absence of a pattern? And so this is what it ended up sounding. We drew no conclusions. Well, maybe one of the interesting things is if we turned up that modulating high enough, it started to sound like a bug flying around your ear, which I don't know, maybe suggests something about bug movement, I don't know, and its relationship to chaotic, I don't know. But you can do all kinds of fun things with this. You can also, I will just mention, we are using direct digital synthesis as a technique for generating audio, but of course the ability to generate sine waves is useful for a number of different applications too. In this particular one, direct digital synthesis is being used to set motor speeds to draw circles, right? And so I'm just making the perhaps obvious observation that the ability to produce a waveform, sine wave or otherwise, of a desired frequency is obviously useful for audio synthesis, but then also generally useful for a bunch of other applications. So this is yet another reason why I stated at the beginning, this is a great one for your tool belt. This algorithm is a great one for your tool belt. Okay. So we're out of time. I will be in lab this afternoon, and I will communicate somehow when the lab hours on Monday will be. Please continue to do the reading. If you have not started doing the reading, please do it. Okay.